Hello everyone, I want to welcome you to my presentation. I'm very excited to present you today the fretting transformer and encoder-decoder model for MIDI to tablature transcription. My name is Sebastian Murgul and I'm one of the authors of this paper alongside with Anna Hamburger, Jochen Schmidt and Michael Heitzmann. This work is a collaboration between the Klangio company, the Technische Hochschule Rosenheim and the Karlsruhe Institute of Technology. This work originates in the master thesis of Anna Hamburger, which I supervised as part of being a PhD candidate at the KIT. And besides that, I'm also co-founder of the Klangio company, which offers tools for automatic music transcription using artificial intelligence. One of our tools is called GuitarToday, and this one is an app that is specialized on transcribing guitar performances into readable and playable tablatures. So the basic process is shown on the right side here. We start with an audio signal. This audio signal is then transcribed into a quantized MIDI signal, and this MIDI is then processed in a way so that we get a guitar tablature from it. And a guitar tablature example is shown here. For those of you who are not familiar with the visualization, we basically have 6 strings which are described with 6 horizontal lines, and the numbers denotes which fret on the guitar you have to press in order to recreate a specific musical piece. Why is this interesting? This is a very interesting problem because we have more than one option to play a note on the guitar for most of the notes. So we have a one-to-n note fret relationship, and there are also some other physical limitations that we have to consider. For example, we can only play one note per string, which also means that we can play at most 6 notes at the same time. There's also a maximum number of frets that our guitar has. The guitar strings can have individual tuning, which can be customized to your needs. There is also a device called capo that guitarists use to transpose their music alongside the fretboard. It basically presses all the frets, all the strings at a specific fret position. And beside that, we also have biomechanical limitations, like the changing of the hand can only be done up to a certain speed. The faster, the more difficult. There are also some positions of the fingers that are easier to grasp and some that are more difficult to do. And there's also a maximum finger span, the maximum amount of frets that you can reach with your left hand or right hand. So common methods today use, for example, graph-based approaches or genetical algorithms. We thought, hey, can't we interpret the task of converting MIDI to tablatures also as a translation task, which could be done with a state-of-the-art transformer model, like, for example, the T5 model, which is basically your vanilla transformer model with some twerks and pre-training. Yeah, and that's the idea. To train our model, we use some datasets. Luckily for us, there is a guitar notation format called Guitar Pro, where a lot of files are available in the internet. For example, we use 3 datasets to train and validate our approach. The first one is the biggest one. It's called DadaGP and has been proposed by Samento et al. In 2021. It contains of about 26,000 tracks that were scraped from pages like Ultimate Guitar and are mostly from the rock genre. And the dataset has a huge problem. because most of the tracks, or some of the tracks, are really handcrafted transcriptions, handcrafted notations with high quality, but a lot of the songs that you find in the dataset have been algorithmically created from MIDI files, which are not very well suited for our deep learning task. So therefore we also added 2 more datasets in our experiments. First of all, the Leduc dataset, which contains 232 jazz guitar transcriptions that were done by Leduc, and all these transcriptions are available on his website where you can purchase them. Besides the Leduc dataset, we also purchased guitar profiles from GuitarToday. This collection contains 363 fingerstyle guitar tabs of popular songs and can also be accessed on their website. So since we now have a Guitar Pro database, we now perform some data pre-processing and preparation and augmentation in order to create our final training dataset. First of all, we apply a data cleaning pipeline where we filter all the tracks that are relevant for our task. Here we focused on acoustic guitar tracks because it's a little bit more condensed than having also electric guitars with 7-stringed and 5-string guitars, which is very hard to also integrate. So therefore we focus on that specific niche. We did some additional data cleanups to remove all tracks that contain too few notes. We tried to remove duplicates and split into train, valid, and test splits, which are then converted into MIDI files, which is used as input into our translation task. We extract from the MIDI and the Guitar profiles all the relevant information, apply an encoding and tokenization scheme. The tokenization is done on a word level, and then we split into subsequences of an equal length for batching in our training. We also apply some additional data augmentation. First of all, we apply a random capo augmentation that transposes the notes across the fretboard, and we do some tuning, random tuning application to have a more balanced dataset that is not that heavy on the standard guitar tuning side. And we saw, or we will see, that this improves the generalization and gives us control to also prompt specific tunings or capo positions. Next, let's have a look at the encoding schemes that we used. We defined 5 different versions. First of all, we have the input side and the target side. The input represents the MIDI, and here we experimented with only adding onset information, adding additional time shift tokens, or even note off tokens. Beside that, on the target side, the main difference is that sometimes we use a separate token for the string and the fret position, and sometimes we use a combined tab and token which contains the string and the fret position. In the evaluation of our experiments, we mainly use 3 metrics. First of all, a pitch accuracy, which sort of checks how good the pitch stays the same in the tablature and also in the MIDI, so we don't want the pitch to change at all. There's also a tab accuracy, which measures how good the tab matches the ground truth. And we also added a playing difficulty metric, which looks at the fret locality, so how fast you have to switch your positions alongside the fretboard, and also a horizontal and vertical stretch, which basically measures or takes into account how difficult it is to do the specific fretting position. So all in all, we get a very good picture of how good or how playable the result is. So let's have a look at the results for the different encodings. Here in the charts you see the tap accuracy for the different encoding versions for our 3 datasets, and we see that version 3 performs the best. This version uses node on, time shift and node off tokens on the input side, and uses the combined tap token and the time shift token on the output side. The second best version ignores the node off token in the input. What works the worst is having string fret tokens separated, where you see a significant drop in our tap accuracies, especially for the DadaGP and the Leduc dataset. Next, let's have a look at the effect of post-processing that we apply. Since without post-processing we get a pitch accuracy of only 97%, which mainly is originated in effects that we have at the windows where we have to combine our tablatures, and to overcome this issue we added a sliding window overlap, so the model has a bigger context or doesn't lose the context of the previous segment in the next segment. This way we were able to push our pitch accuracy to 99.9% accuracy, and the tablature accuracy also increases from 68 to 72%. By also adding a neighborhood search, we were able to, this neighborhood search searches for similar pitches and looks how this pitch is done in tablature when our pitch differs in the resulting tap, and therefore we do a neighborhood search and look for similar notes and apply the same fretting if we don't get valid results. And this way we were able to get our 100% pitch accuracy and do also a little bit improvement on the tap accuracy side. Next, we also experiment with the domain adaptation. Our proposed model has about half the size of the T5 small model, which is available on, for example, Hugging Face. The T5 small model also comes with a pre-trained checkpoint that is pre-trained on a text translation task, and we can see that using a pre-trained checkpoint leads to a lot faster convergence, but using our smaller size model alongside with the Ada factor optimizer, we get a lot better convergence. We also had a look at different NLP task interpretations, because T5 interprets the task as translation. We also explored BERT with the fill mask task and GPT-2 with the text completion task. The T5 approach outperforms all the other NLP interpretations. To sum this up, we also have a comparison with state-of-the-art methods. First of all, we have a baseline method that always chooses the lowest possible fretting position. We also have a star algorithm by Burlet et al. We also use the open source software Tux Guitar in the commercial application Guitar Pro. And as you can see, the baseline, of course, creates very easy to play taps, but our approach outperforms all the other approaches in terms of tablature accuracy. On the upper side of the table, you see the standard tuning without capo. On the lower part of the table, we also added a capo and tuning conditioning, where we included standard tuning, half-step tuning, and full step and drop D tuning. So the model is also able to create taps with a given tuning or capo configuration. Lastly, I also have a qualitative example that shows two main concerns. First of all, Let's have a look at box number 2, where we can see that the A star differs a little bit, and there you can see the main problem that the A star has, because it loses the context after one note and creates some incoherent fretting results. And also when you look at the box number 1, you see that although the fretting transformer results differs from the ground truth, some may argue that the results from our fretting transformer are more playable than the ground truth. Yeah, which is one of the main problems that we have with this task, is that there's more than one possible solution, and maybe a loss which also takes into account the playability would be an interesting extension. To conclude my presentation, I presented to you a tree-5 based transformer approach for MIDI-to-tab translation, which outperforms the baseline approaches. I also showed you a novel preprocessing pipeline with some tokenization scheme that addressed the string-fed ambiguity, and we saw that the model generalizes well across diverse datasets like DadaGP, GuitarToday, and Leduc. And future work could be expanding the datasets for other genres, like, for example, metal, adding musical features like, for example, velocity or the voicing information, and also integrating this pipeline into another pipeline, for example, for quantization, could be a nice extension to directly go end-to-end from unquantized MIDI to tablature sheet music. Thank you for your attention. I'm now happy to answer your questions. Feel free to connect with me on LinkedIn or send me an email.